Hi everyone, welcome back, and we are going to now get into our delete this Unity feedback loop. So it's our first kind of control structure and our control system. We're going to introduce kind of this idea of when you're looking at control systems, usually you can kind of visualize them using like block diagrams. And what we're going to do is actually look at kind of our first feedback loop, feedback system, feedback block diagram. So this is Unity feedback. So this is essentially our system. R is our reference. So that's our reference signal. We're going to kind of just say what everything is first, and then we'll kind of basically connect them and then kind of see what's happening. E is our air. So the air, E is the air in our system. Y is essentially like the system output. So it's like the system response. C is our controller. So C is the controller. So it's what's controlling essentially that system. And it sends U, which is a command output. So from the controller, there's some output command signal, and it influences that is sent directly to P, the plant. The plant is basically our physical system. So for example, if I'm using my favorite example of the kind of mass spring, my mass spring damper system, those equations of motion, this is my plant. So like that is the physical system that I'm trying to control. And I can have, for example, a forcing function that is sending through an actuator like a step response, right? Or a unit impulse of like I'm pulling the system with a certain force, right? So that's kind of the idea there. Let's go back. So the command signal is sent via some type of actuator to the plant here. And the plant, your physical system, responds with some system output Y, and we detect that system response Y with a sensor. So that's how we actually know what that basically Y of T signal is. And that gets sent over here, and we can actually see, we can start to do some what's called block diagram algebra. So my air signal is just equal to R minus Y. We can kind of see that there. So that's really, really critical. It's really important to understand this type of system architecture, this type of control feedback loops, and this block kind of diagram system. So remember, P is our plant. That is our system. That's our dynamic system. And that's kind of the key word there is dynamic that we're trying to control. Y is that measured output. R is the reference or the signal that we want, really. That's the desired output. So if I want my mass in my spring damper system to just be nice and sinusoidal, or if I want to kind of basically fix the position here, like I have some reference signal, some ideal behavior, desired output that I want, and E is just essentially the difference between my desired output and Y, which is my actual output. So C is the controller. The whole idea of this controls class is the goals of our feedback controls is we want the system to be stable. So we want the system to be predictable. We want to control the system in some manner. We don't want that inverted pendulum where, at some point, depending on kind of the control or the input, it just responds exponentially. My pendulum is no longer balanced, et cetera, et cetera. We want excellent tracking. The system output should track that reference signal. The air should be close to zero as possible. That's what we want. We want the system to be robust and be able to basically reject disturbances that are applied to the system. Now, we're going to see that there could be some disturbances that are added to the system. There's a more thorough block diagram systems with disturbances and noise. And for example, in the inverted pendulum case, we want to make sure that, if I blow on it, if there's some kind of disturbance that's applied to that system, that basically it's not going to disrupt that system. So it needs to be robust and be able to reject disturbances. So that's really, really critical. Now, let's do a quick example. And just to kind of get an idea. Think about how we can apply this kind of formalism to a control system. So let's say I want to look at cruise control in a car. So I want to be able to, cruise control is a control system, right? You're controlling essentially the dynamics of that system. So my reference signal would be, again, my desired output. So let's say I want to set my cruise control to 65. So that's going to be that reference signal, right? And actually, I wish we could. I wonder if it's possible. Let me see if I can. I'm going to try to get tricky here. Let's see if it works. Nope, that didn't work at all. What I'm going to do is this. Let's see if I can do a print screen. I'm sorry that I'm just kind of doing something for my own. Okay, here we go. Now we can grab that. Whoops, I don't want to do that, but I want to put it over here. Excellent. Wow, that's fun. I'm sure it's like, this is trivial to you all, but it's fun for me. So our reference would be that 65 miles an hour. Oops, just get back to my. So that's my reference signal. That's the desired output. Air, again, is just the difference. Y would be essentially the actual speed of the car. So measured from some type of sensor, right? So Y would be like the actual, speed of your car. The sensor, it could be, I get it, something where it's reading essentially the revolution of the tires. It could be an accelerometer. It could be, et cetera, et cetera, et cetera. P, your plant, would be the actual dynamics of that car. So you can capture P, the dynamics of the car. E is just going to be the difference from R minus Y. So that's kind of taken care of here. The actuator in this system, or basically your control command, exactly, the plant would be the vehicle. Cruise control will take the signal from the air. And then basically your controller, right? Your cruise, it's cruise control, I don't know why that made me laugh, but it shouldn't have. Your cruise controller will send some command signal U based on that R minus Y input, right? So based on that air, the air gets fed into the controller. The controller then sends some output command, speed up, or to the actuator, which means increase, decrease, and that will then influence essentially the plant dynamics, and then Y changes, and then again, around and around and around we go. You can think of another example. Segway. Segways were, I was sorry. I mean, I know it's horrible. Segway is basically just a fancy inverted pendulum, right? Like the whole idea is you want to, stabilize essentially that stick. The most famous example of an inverted pendulum, I need to add this to my notes. Arrested Development and Joe Bluth. But anyways, I don't want to get too far into this. Actually, shoot, I already have it in there. Use Job image. Oh gosh, I need to fix that. But I definitely need to add that in. But anyways, for copyright reasons, I won't. So inverted pendulum, right? What's the kind of control structure here? So there's some desired angle, right? So I want this angle here to be as close to 0 as possible. That would be my reference. Air, based on sun sensor, again, some type of, again, angle sensor, dynamometer, or not a dynamometer, excuse me. Like, there's tons of different, you could even do it with acceleration, honestly. But anyways, you could do a potentiometer even. But there's going to be some type of sensor that will actually give me my actual Y, right? So depending on the difference, that air signal gets fed into your controller. It could be essentially like the gears of the, basically your motor, kind of similar to our inverted pendulum. The control command gets sent to an actuator. So based on that, control that's built in, the actuator, turns or sends that signal to the tires, and then that affects essentially the plant dynamics, and then back and forth we go. You could extend it to HVAC systems, and then thermal systems in general. They're really important and dependent on control structure because they're difficult to model essentially the plant dynamics. So sometimes you just exit out the plant dynamics, and then you just basically depend completely on your control system. And the reason is because your HVAC people can't do, mechanical engineering, and a lot of these dynamic systems are so well characterized and modeled. Some of the HVAC people need to improve their model. But anyways, we won't get into that discussion. So we'll just enjoy ourselves. We need improved disturbance, reduce steady state air. These are kind of some of the similar things we talked about before. So one more kind of example, because I think it's really important and really fundamental that we hammer home this whole idea of how do we kind of connect between this feedback control and kind of analyzing these block diagrams. So it's really, really, really important. It's going to allow you to kind of visualize the system. We're going to change, we're going to manipulate, use transfer functions. We're going to look at stability analysis, aerodynamics. It's all about the plant dynamics. Is all about this kind of feedback control in this block diagram structure. It's also important to know if we eliminate the sensor and the feedback signal, then we have an open loop configuration. And so this configuration, if you have an open loop configuration, you lack the capability to correct from deviations from that desired and actual output. So I think a great example that's similar to the segue is the following. Imagine, and I did this in class. If you balance a stick on your hand, let's look at how we would analyze this. So the stick, the dynamics of that is my plant. The output would be that angular deviation. So whatever this actual angle is, again, we can measure it multiple ways. And let's imagine first we have some sensor. So let's say I've attached on my hand a potentiometer. I'm measuring that angle, et cetera, et cetera. The reference would be the desired angle, 0, like we've kind of said before. My sensor in this system, or let's say I had a potentiometer, that could be the sensor. I could also have basically my eyes, right? I can look at that angle. My controller would be my brain. The actuator would be the hand. Control input would basically be that kind of signal for the motion, right? To, move and balance the stick. Now, that works. This is a unity feedback closed loop control system, right? To make it open loop, I need to remove, it lacks the capability to basically correct itself. So basically, I'm eliminating essentially this feedback. So here, there would just be a reference, an error, and then you basically, that would be an open loop configuration. So imagine trying to balance that stick and not closing your eyes. Basically, if I remove my sensor, which would be my eyes in this sense, then it's unstable and you're not going to be able to correct. So that's kind of the key idea here. There are, without feedback, inherently unstable systems like the inverted pendulum will not be stabilized and cannot be stabilized. You use open loop control systems in your life all the time where there's no feedback. So basically, your controller just sends an adjustment and it influences the plant, and the output is observed without any adjustment. And your error signal is not computed; it's not used at all. So there are very specific conditions where open loop control systems work, and it's really when the plant dynamics are incredibly well understood, repeatable, and stable systems. Because again, open loop, we can't adapt to any disturbances, any uncertainty, any corrections that can be made. One example is a toaster. Your plant is basically your toaster thermodynamics, right? The controller is your knob. The actuator is going to be the heating element. Your output is temperature of the toast. Reference is essentially the desired doneness, right? No feedback, no sensor. Turn it on, go. Hopefully eat it. But even then, you kind of, maybe it's just me, but, oftentimes my toaster will give me some really nasty burnt toast, so we don't want, open loop can have issues. Closed loop would be better, but it'd be much more expensive for toast. And you don't need to eat toast every day anyways. All right. So next time we're going to get into kind of this idea, and we're going to actually start to then analyze and provide essentially the dynamics of the plant. And we're going to use this example. Of car velocity. And we're actually going to essentially describe the systems. We're going to model it essentially in this time domain. And then we're going to make sure that our mathematical description matches with our understanding of this control dynamics and how the system should behave. So that's we'll actually put this all into focus for a very specific example and work through all the math steps. And also, again, deriving those equations of motion are really, really critical. We need to be able to do this. So really practice well, and I know you'll do great. So see you next time. Thanks. Bye.